Okay, thank you, Rama, and thank you, everybody. Welcome to this lecture. Today, we'll talk about large-scale air-sea interactions related to monsoon and how. But to understand the large-scale air-sea interaction that can influence the variability of monsoon, we need to understand basic how basic large-scale interactions affect climate variability in the tropics in general. So for that purpose, today's talk, I will concentrate mainly on the basics of the large-scale air interaction that lead to what we know now as El Nino and Serrano oscillation. This is a classic example of how large-scale air interactions can produce a climate variability in the tropics. So that is basically, in the next couple of lectures, we will actually talk about the air interactions associated with the monsoon on different time scales. So for that, we need to build this background on how really the large-scale air interaction can produce the climate variability in general. So let us talk about how do the ocean and atmosphere interact in general. So basic fundamental air-sea interaction comes from small scale ocean and atmosphere interactions, which happen basically through turbulent mixing. How does the atmosphere and ocean can interact? It can interact through atmospheric winds that can force the ocean to produce ocean currents, or atmosphere also has heat fluxes. Heat fluxes can affect the sea surface temperatures. Both of these currents and heat fluxes can influence sea surface temperature distribution. And sea surface temperature is what from the ocean atmosphere feels. The surface of the ocean and its temperature produces the latent heat flux and also moisture flux. These latent heat flux and moisture flux can go up to the atmosphere and influence the atmospheric clouds and heating, and thereby affect circulation. So therefore, it is through sea surface temperature that atmosphere feels the ocean, and the ocean feels the atmosphere through the winds and the heat fluxes. Now, how do they actually transmit this information from one medium to the other medium? It is essentially the turbulent mixing in the in the ocean mix layer help transmit the atmospheric momentum. The winds can try to force the ocean, but that momentum has to go down to the ocean, and that can happen only through the turbulent mixing in the upper layer of the ocean. And that so therefore turbulent mixing is important in terms of making the atmosphere, ocean feel the atmosphere. And on the other hand, similarly, the turbulence in the boundary layer can produce heat heat and water flux, water vapor fluxes from the ocean surface. The turbulent boundary can mix that to the atmospheric free atmosphere, to the base of the clouds, and those moisture and heat fluxes can influence the cloud formation and thereby atmospheric heating. So both medium, the turbulent mixing is important in making their presence felt. So therefore that happens in a very, very small scale. So fundamental air-sea interaction does take place in very small scale, but these small scale interactions can also lead to certain amount of ocean atmosphere variability at different scales. For example, let us look at this. For example, evaporation. Evaporation is a function of the atmospheric wind speed, the differences in the saturation humidity at the surface, which depends on the sea surface temperature, and the atmospheric humidity just above it, which depends on the atmospheric temperature at the lower level. So therefore, winds and SST will determine how much evaporation will take place. Now, once the evaporation takes place, the evaporation actually affects the SST. Therefore, the SST cools, and that influences the evaporation again. Therefore, now the moisture can be accumulated in the boundary layer, but therefore in the winds in the boundary layer, if it can converge this moisture, for example, then it will go above the boundary layer and then produce and feed into the clouds. And that can happen through like vorticity associated with synoptic events like tropical cyclones, and they can produce clouds, and those clouds can produce heating, and heating will then produce wind anomalies, and those winds can again influence the evaporation. So there will be a feedback that is possible, and this is fundamentally what happens in a small scale and even on sometimes in a synoptic scale, where synaptic disturbances can influence the small scale the mixing and thereby affect the ocean-atmosphere interaction. But this is an area which is a different, which I am not going to discuss in detail in this series of lectures, because this is an area which is I mean requires a much more detailed discussion. We will assume that basics of this we know. With that. There is, of course, another type of air interaction that is possible on a planetary scale. That is, and that is what we are going to discuss today. But how do you? I mean, how do you? I mean, think about these? What makes us think about these? This is because externally forced the climate. Essentially, the climate is externally forced by solar heating. But the solar major variations in the solar heating are in the Milankovitch time scales like 21,000 years, 42,000 years, and 100,000 years. So climate has this variability in those time scales. But in addition to those variability and the very long time scales, which is forced by major variations of the solar external heating, there are also variability in the climate we see from observations on interannual time scale like ENSO, on multi-decadal time scales like ISMR, and North Atlantic has about 65 years variability. Now, there is no major peak in solar variations in these time scales. The question then here is, then where does this variability in the climate comes from? So these are essentially internal to the climate system. So therefore, these must come from some sort of an ocean atmosphere land interaction that produce these climate variables. Of course, even within these, there are some additional external factors are now coming up, like the aerosols and greenhouse gases. Those can also produce certain amount of external forcing, but it is not obvious that those forcings can give rise to these variabilities. So in exploring these internal variabilities, we have discovered that the Indian Ocean in El Nino and sudden oscillation happens to be one such very important climate variability in the tropics, which happen to result from such ocean atmosphere, large scale, planetary scale ocean atmosphere interactions. And today I will discuss that. What are the principles? How does this happen? And sort of in a sort of elementary way. So first of all, let us start with what is ENSO. ENSO is nothing but, I don't want to go into great details because there are a lot of interesting stuff about ENSO today. A lot of material is there in the net, and you can look at that. I'll quickly go through some of the basics. And so El Nino and sudden oscillation is nothing but a phenomenon where the ocean in the north, in the Pacific, equatorial Pacific, warms up in the equatorial Pacific warms up significantly and every few years, and then followed by a period of cooling in the same region. This warming in the Eastern Pacific is known as El Ninos, and the cooling is known as the La Ninas. And these events are quite sort of equatorially trapped, and therefore they seem to be associated with equatorial dynamics, and we'll talk about that. and they are varying in strength and amplitude, but most of them are essentially located around the equator and has a pretty large spatial scale. It's almost encompasses this most of half of the Pacific, the positive anomalies, and surrounded by negative sea surface temperature anomaly in a horseshoe-shaped patterns, and the opposite in this in the case of La Nina. So these events keep repeating at some irregular intervals, and they seem to have a sort of canonical pattern. Also, the events are not identical from one event to the other, but on the whole, there is a sort of canonical pattern associated with which you can sort of identify by looking at the sea surface temperature anomaly somewhere here. Let us say this area is known as 3, and if you do a correlation with sea surface temperature over the whole region, you have this pattern that comes out, which gives you sort of a canonical pattern associated with sea surface temperature anomalies. That canonical pattern is also associated with a pattern of surface pressures. Now, suppose I take the same sea surface temperature anomaly over this region and correlate with mean sea level pressure over the whole globe, you see a very interesting pattern which shows that whenever there is warming here, there is a low pressure in the Eastern Pacific and a high pressure in the Western Pacific. So the Eastern and Western Pacific associated with this variations of sea surface temperatures in the equatorial Pacific, sometimes positive, sometimes negative. These give rise to a seesaw in sea level pressure in the Eastern Pacific. When it is warm, the Eastern Pacific is low pressure and Western Pacific is high pressure. When it is La Nina, Eastern Pacific is high pressure and Western Pacific is low pressure. So this seesaw continues, and the sea level pressure is an atmospheric component of this phenomenon. So this while the sea surface temperature is an oceanic component of this phenomenon, this is sea level pressure variations can be considered as and the atmospheric component of this a coupled oscillation. And this is why we now call the sea level pressure variations are known as sudden oscillation. So this El Nino and sudden oscillation makes this and so, or El Nino and sudden oscillation and so phenomenon. This is the sudden oscillation is often is identified by or defined by an index called sudden oscillation index, with sea level pressure difference between Tahiti, one station here in the Eastern Pacific, and Darwin as another station in the Western Pacific. So this sea level pressure center seems to be south of equator. That is why it is called a sudden oscillation. And these two pressure differences can be used to define the sudden oscillation index. And this we'll refer to this from time to time. Now, these variations in the sea surface temperature and surface pressures are also associated with sea level variations. So whenever there is warming, the sea level goes up in the east, and then whenever there is cooling, the sea level goes down. And then on the same opposite thing happens in the Western Pacific. Of course, there is also some of equatorial sea level variations which are associated with the Rossby waves, reflected Rossby waves, and which we will discuss later on in the talk. Now, this is an example of how these anomalies evolved during so these oscillations have a period ranging from about 3 years to about 7 years, roughly about 4-year average period. And therefore, the evolution of these sea surface temperatures is rather slow. And they seem to peak around towards the sort of end of the calendar year, around December, January, February, and then and this is kind of evolved over this cycle of variation. So there are different events that do evolve slightly differently. This 1997 event was one of the biggest in the history, and so this is called a super El Nino, and there are a couple of more super El Ninos are now known. And so if I plot an index of the sea surface temperature, say El Nino 3 index, monthly values of that, and then I have a sudden oscillation index, and plot over any length of time, it turns out that they are very strongly correlated. So this indicates that what is happening in the variations in the atmospheric surface pressure, or atmospheric surface pressure is related to everything that is happening in the atmosphere. So the atmospheric variations are very in these time scales are very much correlated with what is happening in the sea surface temperature or the oceanic variations. So strong correlation between these two indicate a strong coupling between the ocean and atmosphere. How they are produced must be related to the one affecting the other. And that there are more evidences of that if you look at the evolution of some of the events and their relationship between how atmospheric winds may be related to driving the oceanic processes, and how that oceanic processes added to the amplification of the sea surface temperature anomaly. This is again in 1997-98 is a very nice example of how some of these things happened. This air-sea interaction sort of evolved. For example, here a few things are shown. The sea surface temperature anomaly are shown from 1996 to 1998 along the equator, ±2 degrees. And along with that, the zonal winds also around that equator are shown here, zonal wind anomalies. So anomalies positive mean westerlies and negative means easterlies. Basic, I'll show you in a minute. And if you remember from the first talk, that the basic winds in the Pacific are all easterlies. So the easterlies mean wind is easterly. Now these are westerly anomalies on the top of that mean wind. So now and this is something called a 20 degree isotherm anomalies. 20 degree isotherm anomalies represents sort of the warm water volume changes. Now, what is 28 degrees isotherm? So some of the people who are not familiar, let me just show you for a excuse me. So this is the temperature cross section in the Pacific across along the equator with depth. So this temperature the contours means it's very warm in the Western Pacific, 29 degrees, and this warm water is deep in the Western Pacific and shallow in the Eastern Pacific, and this represents what is known as the and the temperature changes with depth up to some depth. It does not change very much, but beyond that, after that, it at a particular depth, it sort of rapidly changes, and that is what is known as thermocline. So the thermocline is the region where temperature variations are rapid, and thermocline separates upper mixed warm layer from a cooler lower layer. And 20 degree isotherm is somewhere in that region of the thermocline, or which separates the warm water. So this is the 28 degree isotherm. So the depth of the 28 degree isotherm, this is the mean depth. Now what I am showing there is the anomaly of this depth. Sometimes this mean depth becomes deeper and then shallower, and that anomaly is shown in that picture. So these are anomaly. So this is the time when the mean thermocline depth became deeper. That means the upper layer become warmer layer become deeper, and that deeper signal then propagates into the east in the form of a Kelvin wave. And this deeper signal, so some of the westerly wind bursts. So these are the westerly wind, these are the positive anomalies. Positive anomalies are nothing but westerly winds. Now these westerly winds, this is May, June, so almost about for a month long, these wind persist. This persisting zonal wind at this point, at this region, then this zonal wind, westerly wind, produces in the ocean a Kelvin wave which depends this thermocline and thereby produces this Kelvin wave, and that Kelvin wave then propagates to the east, and then it hits up. The sea surface temperature increases. The increased sea surface temperature and produces heating in the atmosphere. Heating in the atmosphere further produces another wind burst here, and these wind westerly anomalies further produce more the Kelvin waves, and then they propagate east. So, and they build up the positive feedback through which the sea surface temperature amplifies. And so this is best sort of the ocean atmospheric forcing produces oceanic response, which then produces SST variations, and the SST variations then seem to amplify the westerly winds to the west, and those westerly winds further produce ocean response in the way to positively feedback into the sea surface temperature anomalies. And that seems to be a clear example of how ocean and atmosphere are sort of interacting strongly to produce this phenomenon. It's just so empirically you can see this. This produces as so. Let us please remember this climatological picture in the thermocline, and so the ocean it actually acts like a two-layer ocean, and this any perturbations in sort of the ocean waves sort of come out in the form of perturbations on the thermocline. So thermocline becomes deeper or shallower, and that gives rise to ocean large-scale ocean waves, which can propagate to the east and west, and then produce some of the variations. So this was very clearly seen in the 1997-98 event again, where I saw here some very interesting sort of evolution of this, where what is shown here is that both surface temperature anomalies, evolution of the starting from 1997 January, surface anomaly evolution. Anomaly was negative. That means a La Nina was going on, but when this La Nina was going on, this is a cross section of anomalous temperature and the subsurface and the lower within about 500 meters. So within this, there is a positive anomaly across the equator. So this is across the equator. The surface temperature, water temperature anomalies. Anomalies relative to the climatology, which indicates that when there is a cooling going on in the surface in the east, there is a big warm anomaly already developing at the thermocline. You remember the thermocline is like this, from here, shallow thermocline here, and goes the deeper thermocline. And this perturbation is a depending of the thermocline in this region, which gives rise to warmer temperature here, and that temperature is there. Now this, if you go to next month, this anomalous warm temperature moves to the east and continues to amplify slightly. Then the negative anomalies in the east has died down. And now it is trying to outcrop on the eastern equatorial or Pacific Ocean. And so surface temperature has started becoming warm at the surface. And the next month or couple of months, a warming anomaly has started in the east, and this has amplified. So the subsurface anomaly the big anomaly in the subsurface has now amplified. And then it has outcropped in the east and formed an El Nino has started, and this has further amplified. And then it became, El Nino is now almost becoming mature. But when El Nino has started becoming mature, a negative anomaly has started evolving from the west. And that negative anomaly will then, so when it was in the mature phase of the El Nino, when there is a 4-degree anomaly at the surface, it's a really huge El Nino was happening there. Of course, the subsurface anomaly had actually peaked also in the Eastern Pacific, but by that time, a huge negative anomaly was also developing and propagating to the west. So this, and then finally, this negative anomaly will propagate to the west, outcrop, and kill the El Nino. And so therefore, the point is that this involves the whole upper layer of the ocean, and that this coupled ocean atmosphere interaction produces a coupled sort of wave which can take warm waters from the west to the east and influence the El Nino in this manner. So to summarize some of the characteristics of the El Nino, so this is basically sea surface temperature. The sea surface temperatures are very strongly correlated with the pressure seesaw, the sudden oscillation. So SST and sudden oscillation are strongly correlated. They are phase locked with annual cycle. That is one important aspect of this. They have a certain periodicity, but roughly about 4 years, but it can vary from 3 years to repetition time from 3 to 7 years. The strength of the individual events are not identical. Each of the events are different in some sense, but sometimes there are very big events. Sometimes there are one El Nino event can go to a La Nina event without without sort of go to another El Nino event without having a La Nina event in between. So there are cases like that also. So there is certain periodicity, but there is a sort of general oscillation associated with this. So how do you understand this? To understand these phenomenon, we have to understand. We have to keep in mind some of the background that is there in this the Indo-Pacific domain region. And let me just go through that quickly because we have talked about that before. But let me just go through that very quickly. Then I will stop, and then we'll discuss about the theory and other things. So one, as you remember, the mean winds here are easterly. This is the December, January, February. There is some seasonal variations, but throughout the year, the winds are easterly and they are strong in the Eastern Pacific. This is different from Indian Ocean. I will come back to that at some point of time. And what does that do? And how is the mean temperature? Mean temperature at the surface, sea surface temperature, has a east-west asymmetry. It has a warm pole to the west and a cooling in the east. So this is, there is some equatorial upwelling and the coastal upwelling that produces cooling in this region. And therefore, around equator, there is east-west asymmetry. The Eastern Pacific is cool, Western Pacific is warm. So this is important. And if you look at now the subsurface structure and the thermocline, this temperature structure is associated with this picture I have already shown you. So the thermocline is shallow in the east and deep in the west. And whereas if you contrast this to Indian Ocean, it is different. The Indian Ocean has the warmest temperatures to the east and the colder temperature, slightly colder temperature because of the monsoon winds here during summer. On annual mean sense, it is not that different, but it is colder. So the cold to the west and warm to the east and therefore the sloping thermocline is also sloping from west to east rather than east to west in the eastern in the Pacific. So these differences will be also important when we discuss IOD in the next next class. So these persistent winds are very important. These winds are easterly winds are very important in maintaining this temperature, because the winds produce produce a forcing into the ocean and sort of piles up the water in the west. So the sea level in the west is in the mean condition. Sea level in the west is higher than the sea level in the east, and also on the annual mean sense there is net heat flux that is positive to the west, and that positive net heat flux tends to heat the upper layer, and then if you continue to pushing the water and keeping them there, then the warm water depends, and therefore it produces a warm pool to the west, which is deep. So therefore, persistent easterly winds are important in maintaining the mean temperature, and that is very important, and because that is what is the basis for many of the interannual variations also, because this if the easterly mean winds are weakened by some mechanism or by some atmospheric perturbations, then what will happen is that it will not be able to keep the pressure gradient, because it has built up a pressure gradient by keeping by forcing the water and piling up in the western Pacific. That pressure gradient it will not be able to maintain, and therefore it has to relax. That relaxation will allow warm water to move towards the east. So therefore that is the basic that is why the mean is important. And based on this, Bjerknes actually proposed a hypothesis, hypothesis which says that that the mean winds are very important to compute the mean, and even in the mean, the winds keep this temperature distribution. The temperature distributions of the this hot region produces lot of atmospheric convection. The convection produces upward motion. The upward motion produces this upward motion here produces Walker circulation. The Walker circulation produces eastward movement of air upper level sinking in the eastern Pacific. The sinking air then moves again due to the east-west gradient. The wind will then move to the western Pacific and produce sort of amplify the easterly and help them to maintain. So once you start producing a warming to the west by the mean winds, the mean winds will help it to sustain it by through an ocean atmosphere interaction, because warm waters will produce the convection will produce the heating, and that Walker circulation will reinforce the easterlies and maintain it. Now this can actually influence the interannual variation also. Now on interannual time scale, if I now have a westerly wind burst, a sort of westerly wind burst means you add, there are atmospheric phenomena like MJO, which can produce westerly wind patches around for a period of about 15-20 days, of westerly anomaly about 3 to 4 meters per second, and the mean wind in the western Pacific is about 1 meter or 2 meters per second, and therefore on the top of that, if you put this 4 meter per second westerly anomaly, that produces the mean wind actually westerly, and that can influence the ocean very significantly, and that is how a westerly wind burst can produce a Kelvin wave response in the western Pacific, and that And so the westerly wind burst will essentially weaken that wind, easterly wind. Weakened easterly wind will not be able to keep the pressure gradient, and therefore the worm pool will slightly expand a bit to the, sorry, there is a spelling mistake here, expand to the eastward. In fact, it will sort of expand to the east, and therefore the center of the heating will expand to sort of move to the east, and therefore the rainfall maximum will also move to the east, Central Pacific. Then the upward motion is now at the Central Pacific, and therefore the downward motion here, and this downward motion to the west will bring in westerly wind again to this region, and therefore we further weaken the easterlies. So that process will then perpetuate and allow warm waters to move through these oceanic processes of Kelvin waves. And that is what can build up, initiate an El Nino event, and then build up. And later the warm water move or sort of expand much further to the east, just like what happens in an El Nino event. So this is a kind of mechanism which is proposed by Bjerknes in 1969, and now we know that that seems to be a major contributor to formation of not only the annual sort of maintenance of the annual the temperature distribution and the winds, but also these interannual variations. So, okay, where were you? Bjerknes hypothesis. So there is a mechanism by which this can happen in this, and now so so there is a positive feedback that is possible through this ocean and atmosphere interaction. Now, why? How does this happen actually? In this to happen this any change in sea surface temperature must produce sufficient amount of changes in the evaporation, and that can happen only when the sea surface temperature itself is mean is high, because Clausius-Clapeyron is relationship very nonlinear, and therefore when this is mean temperature is rather low, like in extratropics, then the evaporation efficiency is very poor. Therefore, even a change of sea surface temperature up to several degrees will not produce as much evaporation as a half a degree changes in the sea surface temperature that will produce in the tropics. So tropics, that is an efficient process, because the mean temperature itself is like 28 degrees, 27 degrees, and the 1 degree change can produce a huge amount of change in the evaporation. So that change in evaporation may be moisture may be there in the atmosphere, but the moisture has to be converted into heating. To convert the moisture into heating, there has to be uplifting mechanism by which that will take it up, lift it to the level of lifting condensation, and then start producing convection. And so, if the atmosphere is very stable, then this will not happen. So in the tropics, fortunately, the atmosphere is conditionally unstable. If you give a little push, if it goes to about 2 kilometers, and then it can start becoming self-buoyant. And therefore, this can happen in the tropics. Again, this is difficult to happen in the extratropics. So, so once heating is produced in the atmosphere, that can change the circulation. Then circulation, then the circulation can produce surface stress. The surface stresses then can drive the ocean currents. Ocean currents then can redistribute the temperature and change the SST again. So therefore, it is possible that if we can produce enough evaporation, and that evaporation could be converted into heating, that heating can then change the winds in such a way that original initial perturbation or positive temperature perturbation, let us say, that positive perturbation can be amplified by bringing in more warmer water to that region through these winds, and that is possible under certain conditions, and that is when a positive ERC interaction can take place. Now, why this is more effective in the tropics? That is because, as I already said, that the small changes of SST can give rise to a large change in this evaporation, and that is not possible in the middle latitude. Whereas available moisture also can be converted into heating in the tropics much easily compared to that in the extratropics. That is because atmospheric temperature is conditionally unstable. Atmosphere is conditionally unstable, and therefore it can produce this convert this moisture to the heating easily. Whereas in the extratropical atmosphere is sort of basically stable. It requires a much bigger push to produce that condensation. Another reason why the atmosphere, this ocean atmosphere interaction can produce climate variability. Now that is the air-sea interaction, fine, but can it produce variability in the time scale of a year or years, or it will take many years to produce a variability. So in the tropics, this can happen in the tropics. This can happen on the interannual time scale because we have these free Kelvin waves and equatorial Rossby waves, and their phase speeds are much faster in the tropical region, in the equatorial region, compared to the Rossby wave speed in the extratropics. In the tropics, the surface temperature sort of adjustment, the ocean adjustment takes place through these Kelvin waves and the Rossby waves, and their phase adjustment means redistribution of heat, redistribution of temperature in the ocean. Suppose you give a westerly burst, the ocean has to respond to it, come to an equilibrium. How does it come to an equilibrium? It will produce oceanic waves. The oceanic waves will then slosh back and forth, go to the eastern coast and reflect back, and the western coast and reflect back, and then back and forth, and produce a equilibrium. And that is called the ocean adjustment. Now, the ocean adjustment in the tropics can take place through these equatorial waves, and that has a very fast time scale because these Kelvin waves and Rossby waves are much faster in the tropics, in the equatorial region. Now, in the extratropics, you have only Rossby waves to do this kind of adjustment, and there because there are no Kelvin wave, only coastal Kelvin waves are there, no free Kelvin waves. Therefore, the whole open ocean basin adjustment cannot take place through the coastal Kelvin waves. So therefore, only Rossby waves are available, and the Rossby waves phase speed go phase speed and group speed go as 1/y² as you go further to the north or south, and therefore they take much longer. And that is what we have. Here is an example of how sort of how much time it takes. For example, suppose you start in Central Pacific, you take this distance of about 7.5 thousand kilometers, and if you take that distance and the Kelvin wave speed, the first baroclining mode speed is about 2 meters per second. So that Kelvin wave to go to the east and the Rossby wave to come, which is 1/3 the Kelvin wave speed, to come back to that point will take about 6 months. And if the whole basin, if I take, that takes about a year. So within a year, a Kelvin wave can go across the basin and come back, and the Rossby waves can come back and sort of make the adjustment in this period. So that kind of variation can take place in the but if you take go to the extratropic about 40 kilometer, 20 degree north, 20 degree north itself, such a base about 2000 kilometers. If you take about a basin of about 2000 kilometers, it will take 5 years to cross, and that makes a bigger basin will take much longer time. And so the ocean adjustment cannot take place at shorter interannual time scales. So in the extratropics, the ocean atmosphere interaction can possibly produce some multi-decadal variation, but not interannual variation. In the tropics, the equatorial waves make it possible to have ocean atmosphere interaction producing climate variability on interannual time scale. And but for the El Nino, to be as large as we see it, there must be an instability. Without that instability, the El Nino amplitude cannot be as large as we see it in the observations. So there must be an instability in the coupled ocean, and it is the coupled system, coupling between ocean and atmosphere results in this, but there must be some coupled instability which amplifies it. So this question can be addressed by a simple ocean atmosphere coupled model. So this is, you remember our Gill model. So this is an atmospheric model which is forced by heating. Now instead of steady state, I am using a sort of time dependence because we are talking about slow time scales, and then the ocean model has similar. This is again can be considered a reduced gravity model, where the two-layer model, there's a vertical structure. You remember we had considered the first Veloclinic mode vertical structure for the atmosphere. Therefore, we had this horizontal structure equation. Similarly, the ocean also, two-layer ocean can be considered a given vertical structure is very sort of normal to consider it, because we know that there is a warm upper layer and a cooler lower layer. So with this kind of an ocean, the equations are also are similar to these, the reduced gravity equation. So here the ocean is forced by the wind stress that is coming from the atmosphere, winds, and the heating has to come from the oceanic temperature. But temperature in this model, temperature is made proportional to this thermocline height, because as I showed you, the thermocline height variations result in surface temperature. Not always, but largely it does affect, especially when the mean thermocline itself is shallow, just like in the Eastern Pacific. The change in thermocline height itself can give rise to a sea surface temperature variation. And then you can make the heating proportional to the sea surface temperature. Sea surface temperature, and therefore you can couple them, and we can understand, we can study in a different ocean model. You can couple where temperature equations can be more realistic, where advection by currents of the mean temperature differences in the east-west can be included, which is more realistic. And you can use these, and the wind stresses are proportional to the atmospheric wind. This U and V should be capital U and V. So, so with that, you can actually solve this equation and see, find out if there is an unstable mode. And people have done this kind of study, and there is a lot of studies, and it can be shown that that there is a unstable mode, and that is the Berkney's hypothesis qualitatively shows that there should be a positive feedback. And but how do we quantify it? You can quantify this with this kind of an analysis, and so that there is a very slowly, this is the real part of the frequency, and the imaginary part indicates the growth rate and so on. So from this study, one can show that there is a slow mode which has a significant growth, which can be related to the growth of this El Nino and Southern Oscillation phenomenon. So there is a mechanism that ocean and atmosphere can indeed become unstable in the tropical Pacific basin. So there are still questions, of course. How does it then reverse? Because there is an instability, okay, and the coupled ocean atmosphere interaction then can produce and amplify this. If it is a positive feedback, it should go on amplifying, but it does oscillate, it does come back. Now, what produces the reversal of this growth? So there must be a negative feedback somewhere, and that we did not know initially for some time, but now we have an understanding of that. And so that is what is known as a delayed oscillator hypothesis. So what essentially, and another question is what produces the Fourier periodicity, and these two things are actually related. And the other thing is also that what triggers it. So these are a few questions that also need to be answered. And finally, I mean, one of the questions is the general sort of average period is about 4 years, and that average period we need to explain. So it is the equatorial waves themselves can actually explain this. Now, there is a this is something that we have already discussed before, that the Kelvin waves propagate along the equator, Rossby waves also eastward, Rossby westward, and equatorial waves travel 3 times, the Kelvin wave travel 3 times faster than the fastest equatorial Rossby waves. These are something that we have already discussed them. Now, suppose you have these a westerly wind burst here in this consider an ocean model where you produce a westerly wind burst and sustain it for some time, and that westerly wind burst will produce oceanic Kelvin wave response and oceanic Rossby wave. This is downwelling Kelvin wave. That means it will depress the thermocline and increase the temperature to the east. And there are upwelling Rossby waves, which then start to propagate westward. Upwelling Rossby wave will have upwelling thermocline perturbation associated with this. Now, these waves then propagate as time goes. They will propagate. The Rossby waves will propagate slowly to the west, and the Kelvin waves will propagate to the east, get reflected from the eastern boundary, and as Rossby waves, and then and because they there is no equatorial wave, I mean Kelvin kind of wave that can propagate from the equator to the east. So they have to come as Rossby waves. So the Rossby waves will come up with a downwelling perturbation, and these Rossby waves will come back later on, reflected from the western boundary as upwelling Kelvin waves. And when this upwelling Kelvin wave reaches here, they will they will affect the Kelvin waves, which has a warm part, sort of positive SST anomaly perturbation in this. So the positive increased SST will then can be reduced by the downwelling Kelvin wave that arrives here. So this is the delayed negative feedback Latin mechanism. So if there is no coupling, this initial perturbation will move back and forth and then decay. But what happens in this the positive, the instability is there. So this heating, as it propagates, it also produces heating in the atmosphere and amplifies these Rossby waves and then creates more Rossby waves to propagate and produces a new Kelvin wave to propagate to the east, and therefore amplifies it. And that is what this produces the instability. So therefore the waves themselves can produce an instability, and the waves themselves will generate these Rossby waves, which will then come propagate back and to the west and come back, reflect back and come back to this region where with an opposite sign can then start killing the instability. And that is the negative feedback that is associated with this. So a positive feedback which gives rise to the instability, but associated with the winds and the ocean perturbation, ocean waves that are generated by the winds can give rise to a negative feedback through a delayed mode, which can then bring it back or contain the instability and bring it back to the negative phase. And when negative phase happens, these waves will have an opposite sign. They will then create and Rossby waves of opposite sign, which will then come back and then start decreasing, sort of depressing the thermocline in the central Pacific to further produce a new event. So that way they can oscillate. So there is a mechanism by which this is known as a delayed oscillator theory. This can be represented by a simple equation where this represents the rate of change of temperature or the sea surface temperature. If nothing was there, this will represent a growing solution, right? That is the instability. So this is the coupled instability. Now this part represents a delayed negative feedback coming from depending on this temperature produced a wave which is affected as some time back. That temperature effect will affect today's temperature because some temperature wave a few months ago produced a wave which will come back and reach today and affect the temperature and this. So this is how the negative feedback can take place. And there is also a thermocline and non-linearity which comes associated with the thermocline variation, thermocline wave, which can also give rise to the modification of the amplitude. And so this can actually explain the periodicity as well as the amplification. And therefore, the basin size is very important. The Pacific basin being very big, it gives you that much time to grow and then to a large amplitude, because the delay, the time for the Rossby waves to come back and start killing it takes certain amount of time. The delayed feedback requires time. But in the Indian Ocean, for example, which is 1/3 the size of the Pacific, then if such a perturbation is produced, the return time will be much less, and therefore the period itself will be curtailed. At the same time, the amplitude of the oscillation can also be lower, and that is what we'll discuss in the next class. There is another way of looking at this. This is called the research discharge theory of El Nino. This is not very different, but looking at it by in a different way, and trying to combine the atmospheric forcing and the oceanic the transports in a consistent way, which is there in a way in the delayed oscillator model also, but now you are adding a little additional component, which comes from the observation that if you look at the warm water volume, the warm water volume is the integral of this Z20 means this is the depth of the 20-degree isotherm. This depth of the 20-degree isotherm, if you integrate over the whole domain, east, north, south, and east-west direction around the equator, and then plot it with time, it turns out that becomes maximum before an El Nino event actually happens. So it is always the warm water volume maximum precedes an El Nino event. And then when the El Nino happens, this goes down. And then again it comes up. So the warm water volume maximum means what? That is the whole tropical belt has become warmest. The tropical the ocean, upper layer of the ocean has become the warmest. That means it has got recharged. So this is a place where this is called a recharged place. The upper ocean become recharged, and when it becomes recharged, it becomes susceptible to some perturbations, which will then start discharging it, and then that discharge actually leads to the El Nino, and the El Nino when it starts, that perturbation produces the El Nino starts producing the discharge, and that discharge then takes it to a lower side of the and takes out the warm waters away from the equatorial belt and makes the equatorial region low in warm water volume. And then again some opposite thing will start producing recharge and picks up and pick up at some point of time. When it picks up, again it will be followed by an El Nino event, and which will then discharge it and then take it. So this is a sort of process of recharging and discharging of the warm water volume. Now, how does it happen? It happens through something called the sort of transport. So, excuse me. So, if you remember, so the SST, this produces the when there is a SST perturbation, like the when westerly burst producing an SST perturbation, to a positive SST anomaly to the east, that positive SST anomaly to the east produces heating in the atmosphere. The heating in the atmosphere produces Rossby waves, Rossby waves to the west, and westerlies to the east, and there is something Rossby wave perturbation to the west, north and south. And these Rossby wave perturbation produces those Rossby waves in the ocean, and that Rossby wave perturbations, actually atmospheric Rossby waves, produces Swadroop transport in the ocean. Swadroop transport is nothing is proportional to the curl of the vertically integrated meridional transport in the ocean is related to the curl of the wind. And that curl of the wind associated with those waves is essentially produces this Swadroop transport. Swadroop transport is nothing but sort of it takes away the sort of mass away from the equatorial region during that period. Warming warm anomalies during the evolution of the El Nino, and that discharges the and when it discharges and it becomes a negative anomaly in this region, then you have the cooling anomaly. The cooling will have opposite atmospheric response. The opposite atmospheric response will produce Swadroop transport towards the equator, and that will then start recharging the ocean. So these are not independent of the delayed oscillator, but so therefore people are now trying to combine these two both and coming up with what is known as a unified model of the El Nino. So some of the things, what triggers it is still not very well understood, but westerly wind bursts are very, very good examples of which can do it, but not all westerly bursts but lead to an El Nino. So there are issues that we need to clarify. This is what I have already shown, how the westerly wind bursts can produce, but the conditions of the mean in the ocean has also to be right, so that that it can lead to the instability. Kelvin waves bursts will produce westerly bursts will always produce Kelvin waves, and the Kelvin waves will propagate, but they may not lead to the instability. If the instability has to have the instability sort of feed back into the atmosphere and produce it, requires the mean conditions of the ocean to be right, and that is what is those if the atmosphere the ocean was at a recharged state, and then this perturbation take place, then will generate this. If it is not in the recharged state, it is in the process of recharging, then these ocean perturbations will not produce an instability or instability of this kind, and therefore lead to an El Nino event. So there is, of course, that can still produce a sort of different the other part of the negative feedback. Okay, so there are different these theories of El Nino, different theories, as I mentioned. Delayed oscillator is one, recharge oscillator is another. The Western Pacific oscillator, advective reflective oscillator, some few other names are given, and there is the people are now trying to unify them. So I'm not going to go into all the details right now, but I want to just highlight a couple of things that we have discussed. Basically some sort of a sort of canonical picture, but the El Ninos are not identical. there are different sets of El Ninos, and people have now found that there are some El Ninos which the SST anomaly becoming maximum in the Eastern Pacific, and some El Ninos where the SST anomaly is in the maximum in the Western Pacific. Okay, sorry, the Central Pacific. So these El Ninos are known as CP El Ninos, whereas the ones that produces anomaly in the Central Pacific are called CP El Ninos, Central Pacific El Ninos. So there are at least two sets of El Ninos are known, and there are a few in between. So these now, therefore, we cannot club all the El Ninos into one kind of category. We must understand what produces, why one is maximum, sort of maximum anomalies are in the central, and why in another it is in the eastern. So these differences need to be understood. So basically, and all this event-to-event variability is now considered called ensodiversity. And people are trying to understand this ensodiversity. Still, there are issues. As I said, as in the most cases, we have understood some of the linear aspects, some of average aspects of El Nino. But now we are trying to understand some sort of a non-linearity. This event-to-event variability is some sort of non-linearity, which is still not well understood. And people are now trying to quantify this. What is this ensodiversity? How can we quantify it? This is also called complexity. So there are studies which have now come up with talking about complexity, and which is nothing but this ensodiversity only in a different form, and trying to quantify it, and so that how it affects the predictability, because predictability is ultimately if the event-to-event variability is very large, and then we don't understand, then our predictability will be limited, because it is the regularity which is predictable. If it is too much irregular, and if we don't understand how to capture that, then obviously models will also fail to predict them. So now the current effort is to understand this diversity of the El Nino, or this the complexity, and that is the sort of current area of research. I will not go into great detail again, because we have also did a little study just to try to understand this complexity or diversity. This seems to be associated with three different modes of El Nino. So there are sort of three. If you can decompose El Nino time series, sort of assess the variability in this region into three different modes. One is a sort of in temporal domain. There is a biennial mode, there is a quadrennial mode, and there is a sort of this quadrennial mode has a sort of decadal variation with it, and that these three modes, you can all the different the super El Ninos, the different shades are essentially a combination of these three. So different at some if you add a different proportion of these to essentially give rise to different all the variability. But the question still remains is that why in a given event the contribution of these three different modes vary, and that is still an open question which we need to understand. So with that, I think I have come almost to the end of this. There are some few reviews I have summarized here. So we also did one last bit of information. This is just we did a bit of study sometime back, way back actually in 1991, I think. I have not written it here. We looked at the predictability of this. So this variability is, of course, is related to the predictability of what is the limit on predictability of El Nino, because we know that this is a slowly varying phenomenon. So there must be certain can we predict how far ahead can we should be able to predict? For that, we need to, just like in atmosphere, we have done predictability studies, and we know that in the extratropical atmosphere is predictable up to about 2 weeks in advance. That is the limit on predictability. But what kind of limit is there for predictability? Climate, for example, and so is a good example of climate. So we did a study using a coupled ocean atmosphere model, and which had this is a model known as the Ken-Zabiak model, where there is an atmosphere which is a steady state atmosphere, and they mix and the ocean which has a reduced gravity ocean here, and the ocean mixed layer. This model was very one of the very earliest coupled ocean atmosphere model, which could simulate the El Ninos and sudden oscillation reasonably well. The anomaly of the El Nino sudden oscillation phenomena very well, and they actually made prediction way back in 1986. So we used this model to estimate the limit on predictability on the ocean ENSO. And to do that, we carried out a series of prediction experiment using the model, and then the predictability experiments, so the identical twin experiments to find out how small errors grow. The actual prediction experiments indicated that there is something called predictability, spring predictability barrier. So if I plot the dependence of the RMS error of the predictions as a function of the initial conditions, which is pairing with the month of the year, sort of calendar months, then it turns out that the errors grow pretty fast around the spring time, and becomes as large as the signal by about 4 or 5 months. But on the other hand, in the winter and in autumn and specifically in winter, northern winter, that can extend up to about 9 months or so. So there is longer prediction scale during winter, and there is poor prediction scale in the summer. So there is a, now it is known as a this phenomenon is now known as a spring predictability barrier. But apart from that, what we wanted to do is first estimate the growth of small errors in the system, and to quantify what is the error growth in this system. To do that, we have carried out a series of identical twin experiments. And identical twin experiments are like you make a long control run, and from the control run you pick up some initial conditions, and those initial, you perturb the initial condition, run another prediction experiment about 15 years. And like that, we did about 181 pairs of identical twin experiments. And then from the divergence of the trajectory, you can find out RMS error. And you can average RMS error if you plot from all these experiments. It shows the error growth in this form, in this manner. It shows very interestingly that the growth of error has 2 time scales involved in it. One time scale, so I can fit a model, error growth model with these, and that turns out that there are 2 time scale. One time scale where the initially error grows pretty fast, and that seems to be associated with the coupled instability in the system, and is consistent with the doubling time of that error is about 5 months, is consistent with the coupled instability of the system. And the other slower time scale has a doubling time of about 15 months, which is consistent with the slow oscillation of the whole ENSO phenomenon. ENSO phenomenon has a slow 4 to 5 year oscillation, and this 4 to 5 year oscillation itself has a modulation, modulates the growth of error at a slow time scale, and that is given by this. And this is for I think this was a kind of early, first study in that direction, and people have now used the error growth models like the linearized equations and find out Lyapunov exponents and all that, and then consistent these results are found to be very consistent with those theoretical studies, and therefore this seems to be a fundamental sort of result in terms of the predictability of the climate. So from these we can make an estimate of what will be the limit on the predictability, just like in weather system. If I assume that there are certain in our assistive and the NINO3 sea surface temperature anomalies, there is some fundamental limit on observational inaccuracy, let us say about 0.25 degrees. And suppose that initial error, if I use to and ask that question, how long it will take to for the errors to grow to about to the level of the signal of about one more than 1 degree, which is the standard deviation of the signal. And it turns out that that actually is almost about 3 years. So it is possible in principle, that the El Nino should be predictable up to about 3 years, or 2.5, 3 years ahead of time. But today's scale is still limited to about 6 to 9 months by models. But some models are now beginning to show sort of improve them to 1 year. And as Professor Narasimha has asked earlier in one of the talks, that how we can use the AI/ML to improve this. People are now using that in prediction, ENSO prediction. And in fact, they have used, by using the model data to train the AI/ML model, they have, one study has shown that they can improve the prediction scale all the way up to about 1.5 years, compared to about 9 months, 10 months by the dynamical model. So there is a scope for further improvement of these, the dynamical models prediction skill, as well as probably further improve them by using this AI/ML model. So, okay, with that, I'll stop.